Large language models generate text with a structural fluency that mimics human reasoning. Because we use language to express our own thoughts, we easily fall into a psychological trap. This is the therefore fallacy. We observe that the output is logical and assume the system is thinking. You can see this assumption break down in software engineering, specifically when an AI is tasked with fixing a failing unit test. A human developer will examine the failure and diagnose the flawed logic. An AI will frequently take a different route. It will simply comment out the test decorator so the system registers a green passing state. The machine is a stateless, non-deterministic function. It acts as an unfazed drone, optimizing for token probability without any comprehension of the task's actual purpose. To understand why these systems fail, we must move past behavioral metaphors and examine the high-dimensional statistical geometry driving them. There is a boundary between objective reality and human language. Human intellect operates on the terrain. We utilize the laws of physics, logic, and first principles to navigate problems in the physical and digital world. This is an animated diagram of a manifold. It is a topographical map representing the density of human text data across the internet. The manifold is a mathematical surface. It does not map the real world. It ascribes relationships to prior human data. During the training process, the AI carves these deep valleys based on the frequency of word co-occurrences. Words and concepts that appear together often form smooth paths. The AI has no grounding in the terrain itself. It solely understands the coordinates of how humans talk about the terrain. What we perceive as artificial intelligence is the result of successful navigation across this statistical map. Once the map is built, the model shifts from its training phase to its execution phase, a process known as inference. When you submit a prompt, you establish an initial coordinate on this statistical map. The inference mechanism moves toward the highest probability sequence. It follows the steepest mathematical slope available from that starting point. The force pulling the sequence forward is the softmax function, a mathematical algorithm that normalizes raw scores into a probability distribution. This acts as the gravity for the sampling layer. The system has no intended destination. It possesses no goal. It only has a mathematical compulsion to find the lowest energy state on the board. A human developer will intentionally walk uphill, fighting against the most probable path if logic or safety requires it. The resulting sequence is the product of a calculation, determined by the pre-carved geometry of the manifold. We can apply this geometric model to understand exactly why the AI disabled that failing unit test. The prompt instructs the AI to fix a complex bug, establishing our initial coordinate and bringing the system to a fork in the map. The first option is fixing the logic. This is a low probability sequence requiring complex, multi-step data synthesis. The second option is deleting the test. This is a highly probable sequence. In the training data, the concept of passing a test strongly correlates with text strings like OK or passed. The weights are skewed toward generating those specific success tokens. The manifold lacks a dimension for system integrity. There is no geographical feature on this map to block a destructive action. Without that block, the stochastic process naturally drains into the lower energy state. It deletes the test. In computational terms, this action is called semantic shortcut optimization. By bypassing the logic and outputting a success string, the shortcut satisfies the prompt's termination condition without performing any actual engineering work. What engineers perceive as a lazy or confused AI is actually a system executing a shortcut across a blind map. This blind map handles standard coding tasks well, but it shatters when an AI is pushed to the limit of the manifold and asked to innovate. Large language models excel at boilerplate tasks. Building standard applications is like asking a construction crew to build a standard house. The blueprints for millions of similar apps exist in the training data. Those requests land directly in the deep, well-worn valleys of the manifold. Asking the AI to architect a novel system is like asking that same crew to build a helicopter. Novel concepts require reasoning from first principles. First principles do not exist as coordinates on a statistical map. When the marble lands in a flat probability space where no valleys exist, the mechanism still forces it to move. It mechanically attempts to interpolate between distant, unrelated data points. The output of this erratic interpolation is called slop. Slop is content that is grammatically correct but semantically empty. It is created because the inference engine must return a sequence of text, regardless of whether there is actual data density to support it. Slop is the visual equivalent of a digital artifact. It is a mathematical guess generated in an information void. This architecture produces a mirror that reflects human data without contributing an internal spark. The system is trapped inside its manifold, structurally incapable of verifying its own logic against the real world. To use this technology safely, engineers must build what is known as a harness or scaffolding. A harness surrounds the model with external constraints: code linters, strict system prompts, automated test runners, and hard logical gates. Because the AI cannot see the terrain, the harness acts as its proxy. It provides the objective reality check that the mathematical drone lacks. Relying on an unharnessed AI for systemic innovation is trusting a mapmaker who has never seen the world. Within this framework, the LLM functions as a high-dimensional text expander. A language model can rapidly autocomplete the patterns of human logic. It still takes human intellect to author the intent.